Chapter 18 talks about electrochemistry. And electrochemistry is very important to your everyday life because this society is starting to run more and more on batteries. And electrochemistry is the idea and the principles behind how batteries work. As always, there's some suggested problems for you at the end of the chapter that you can take a look at. Electrochemistry is the study of redox reactions. And through the use of redox reactions, we can have electrons flow. And that flow of electrons is an electric current. If you remember back to the first semester general chemistry course, redox reactions stand for oxidation and reduction. We can't have one without the other, and this happens when we transfer electrons from one element to another element. And this transfer happens in an electrochemical cell. It's where we convert chemical energy into electrical energy through that transfer of electrons. If they're spontaneous, we call that particular cell a galvanic cell or also a voltaic cell. Both of those words get used interchangeably. If it is non-spontaneous, we have to apply an electrical current in order to make the reaction happen, and that is in an electrolytic cell. So electrolytic cells are used to recharge batteries. They are also used to plate different metals onto surfaces. So if you have any jewelry that is silver plated or gold plated, that is carried out in an electrolytic cell. We need to remember our oxidation-reduction reactions. So remember that when we transfer those electrons, that's when we have redox reactions happening. And atoms that lose electrons are being oxidized. Atoms that gain electrons are being reduced. And we have mnemonic devices that we can use. So oil is oxidation is lost. Reduction is gain of electrons. Or if you prefer, you can use Leo the lion says grr, which is loss of electrons is oxidation, gain of electrons is reduction. And that just helps you remember which one is which. So if we increase an oxidation state, it is oxidation. If we decrease it, it is reduction. So we have an example where we're taking sodium metal and chlorine gas producing sodium chloride. If we look at sodium, it is going from an oxidation state of 0 because it is the elemental form. So our oxidation state is 0, and we lose an electron, becoming a +1 oxidation state. And so because we're losing an electron, that is our oxidation. Our chlorine gas, chlorine is the elemental form, and it's gaining electrons to become negatively charged. And so because it's gaining electrons, that is undergoing reduction. We need to remember how to assign oxidation numbers. And for the most part, it follows the rules of charge. So if you have a metal with a +2 charge, your oxidation state is a +2. If you have a neutral compound, all of the oxidation states have to add up to 0 for the compound. If you have an ion, all of the oxidation states have to add up to equal the charge on that ion. These are theoretical rules that help us decide where the electrons are found in our compounds. And they help us keep track of those electrons as we move throughout a chemical reaction. When we get to strictly non-metal containing compounds, the rules get a little more complicated. So the higher you are on this table, the higher priority it is to follow that rule. So if you have a fluorine containing compound, the oxidation state is always a -1. If you have a hydrogen containing compound, the oxidation state is always a +1. When you get to oxygen, most of the time oxygen is a -2, unless we have other circumstances like a fluorine or a hydrogen that take priority. And as we move further down the list, then it's less priority for those ions or those elements to retain those particular charges or oxidation states. So let's give this a practice. Pause the video, see if you can remember what is oxidized, what's reduced, determine what the oxidation states are, and label the oxidizing agent and the reducing agent. So let's start with oxidation states because that helps us to determine the rest of the information. So if we have zinc with no charge written, its oxidation state is going to be 0 because it is in its elemental form. How about hydrogen? Here we have hydrogen. We know the charge is +1 for hydrogen. That means each hydrogen is going to have an oxidation state of +1. Now we have zinc 2+. What is our oxidation state for zinc 2+? It's going to be equal to the charge, which is a +2. And hydrogen, H2, this is the elemental form. And so for elemental forms, our oxidation state is 0. Now let's look at what is oxidized and what is reduced. So we're going to compare the same element to each other. So we're starting with zinc, neutral, metallic zinc, going to the zinc ion. We're going from a 0 to a +2. That means that it has lost its electrons. Oxidation is loss. And so our zinc in this case is oxidized. If we look at our hydrogen, we're going from a +1 to a 0. That means that it's gaining electrons to become neutral. And so this is the reduction. Our H+ is reduced to become hydrogen. Now how about the agents? So what is our oxidizing agent in this case? Our oxidizing agent is the H+. Now why is H+ the oxidizing agent? We said it was reduced. Well, because it is reduced, it's causing the oxidation. It's making the oxidation happen. And so that is why it is our oxidizing agent. Our reducing agent is the zinc. Because it is oxidized, it is causing the reduction to happen, and so it is the agent. Here is a list of common oxidizing agents and common reducing agents. Now, if you look at the list of oxidizing agents, what do you notice about many of the compounds on the left-hand side? Well, many of them are oxygen-containing compounds. And how about the compounds on the right-hand side? Well, these are a little more diverse, but many of them contain hydrogen. Now there is no need to memorize these lists, just showing you some common things that you might notice. So oxidizing agents tend to have oxygen in them. Reducing agents tend to have hydrogen. In the compounds. And you'll notice that hydrogen peroxide, because it contains both, it can act either as an oxidizing agent or a reducing agent. Now, when we're measuring these cells, there's a couple different things that we can measure, and one of them is electrical current. So in order for our cells to work, there has to be a flow of electrons. And that flow is going to happen through a conductor, usually electrical wires. And we can think about this similar to the flow of water. So the flow of water is going to move in the direction that's easiest for it. So typically that's downhill in response to differences in elevation. Well, electrical current is similar. We're going to have the flow of electrons, and it passes through a given point at a time, and it's going to flow from a higher potential energy to a lower potential energy. We can produce an electric current flow simply by putting two different metals in contact with each other. So if we take a zinc piece of metal and we put it into a copper solution, there is a flow of electrons from that zinc metal to the copper, and we will actually get copper metal that forms on the surface of that zinc just by putting those two solutions together. So we get an electrical current flow. Now this is interesting, but not as helpful or useful as if we can gather those electrons and allow them to do some work for us. So if we want to measure the electric current, that is measured in a unit that is called an amp. An amp is the electrons that flow through a system every second. And we can think of those electrons as a coulomb. So coulombs is a measurement of the flow of electrons each second. We can also measure the potential difference. And this is a difference in energy between the reactants and the products. And the unit that we use in order to measure our potential difference is a volt. And so 1 volt is equal to 1 joule of energy per coulomb of charge. And this is what is referred to as the electromotive force. It's the amount of force pushing those electrons through the wire. When we measure a cell potential, that is the difference in potential energy between the anode and the cathode of a voltaic cell. So voltaic, remember, are spontaneous cells. And that cell potential is usually represented by an E. So a voltage reading that is E. It depends on how easy it is for the oxidizing agent to be reduced at the cathode and the reducing agent to be oxidized at the anode. So it depends what materials your cell is made out of as to what that standard cell potential is going to be. So remember that when we're measuring the cell potential, that E stands for voltage, and the little degree sign, that tells us that we're under standard conditions. And standard conditions, just as it has been for many of the other topics we've talked about, is 25 degrees Celsius, 1 atmosphere for gases, 1 molar concentration for solutions. And if we add the cell potentials for the half reactions, that's how we come up with our E cell for our voltaic cell.